the QMSS class 5065, Bayesian Statistics for the Social Sciences. So if you've come to the wrong class, might as well stay at this point. Might learn something. Okay, let's get it going. So here's a plot, two plots from a recently published article in 2019, chronicling the rate of articles, published articles that use Bayesian analysis over a few decades. And so let's start by looking at the purple line here, which corresponds to the number of papers in applied statistics journals that use Bayesian statistics. You can see that in 1980 and whatnot, it's fairly low. All of a sudden in 1990, it shoots up, like quadrupling the number, and increases steadily from there. So you might ask yourself, and if not, I'm asking you, why do you think that is? Internet. It has to do with computers. This is almost pre-internet. This is like AOL and a bunch of other things that have since gone out of business. Yes?
The use of machine learning has increased slowly last decade.
Certainly, that's also true. I would say machine learning would have a little bit later start to its takeoff and trajectory using different sorts of techniques there. Yes?
More data, but not enough data for ML. Or, yeah, like the right in between Goldilocks and enough data.
That's a possibility. Certainly got more data that you could like download over AOL and start to use it. Yes? Yes?
Just computing innovation, more computing power so you can actually run them.
Yes. Hardware is a big part of this story. By 1990, you would start to see some of the younger, cooler professors having a computer in their office. Some of them. But hardware is only part of the story. Does anybody else have some thoughts about that? Yes?
It was embraced by the academic community. Like it went from being controversial to being like a sort of more accepted. And I think in the 90s it was when like Microsoft, computer scientists at Microsoft started really using Bayes to innovate.
Yeah. Acceptance of Bayesian stuff. That's also definitely a part of the story. So lots of parts to the story. Anybody else want to jump in? Biggest part of the story, an article was published in the Journal of the American Statistical Associations by Smith and Gelfand that proposed an algorithm to do Bayesian analysis that overcame the hurdle that prevented Bayesian analysis from being prevalent in previous decades and even previous centuries. So 1990 marks the start of modern Bayesian analysis, which uses computers and it uses random number generators, random number simulations of random numbers in place of calculation of integrals, which had proven to be in many cases impossible. So prior to 1990, you had ancient Bayesian analysis, which established a lot of good, albeit controversial, theory, but Bayesian analysis was impractical for a lot of the most of the problems that researchers were interested in tackling. And although it's not depicted here, it's worth keeping in mind that non-Bayesian analyses started to be computationally feasible on computers around 1970, I would say. And so that 20-year head start, I think, has a lot to do with the patterns that we see, 20, 30, 40 years subsequent to this and off into the future. So it is an idea, a paper, an algorithm. That algorithm got implemented in software for the first time, starting in 1990, along with the development of hardware to be computers that are faster, had more memory, could analyze more data, led to this rapid and sustained increase in articles in statistics journals using Bayesian estimation techniques. All right? So that's all well and good, but then you might ask yourself, looking at the non-purple lines on this picture, which depict the use of Bayesian estimation techniques in various fields of the social sciences, and you see that it is not nearly as pronounced or as extensive an increase in the rate of usage of Bayesian techniques. And you might ask yourself, why is that?
It might take time for like the theoretical work to actually filter through to some of those disciplines.
It does, but it's been like 30 years now. And if anything, yeah, still, pretty low. So yes, it does take time. But like I said, the theory had been established in like 1780. We're just waiting for the algorithms, the software, the hardware to come and make it possible to do these sorts of Bayesian analysis. And it caught on like wildfire in statistics, applied statistics. But why not in the social sciences, which are basically a branch of applied statistics? Yes?
Is it possible that it's still difficult to really break the mold of traditional techniques and methods that these sciences are using?
Yes, that is certainly part of the story. So how many of you took Intro to Data Analysis in the QMSS class last semester? Almost everybody. Okay. What textbook did you use for that class?
Older econometrics.
Yes. And so what did you think about the Bayesian chapter in that book?
We mostly talked about the regression, so.
Yeah. So that chapter didn't exist.
Yeah.
It's kind of the right answer to that question. Is there a section on Bayesian analysis? Did the word Bayesian appear in the whole book? How many pages is that book?
600-ish, I think.
Hundreds, if not 1,000. How many editions of that book have been written? 7 or 8 by now? That is a deliberate omission. Now, Jeff Wooldridge has written about why he prefers non-Bayesian approaches on Twitter, and he has his reasons for that, but does not state them in the book. Doesn't even mention it. So if it's not taught, if the people who write non-Bayesian books actively don't want to mention it in introductory books, how would social scientists ever know how to use those techniques? So how many of you all took theory and methodology last semester? About the same number. What textbook did you use for that class? Went through a whole semester, didn't manage to learn what the textbook was?
It has mostly articles.
Mostly articles. Still using Straits and Singleton? No? Okay, well, to make a long story short, that's another book. It's like Theory and Methodology for the Social Science 6th edition. Does it have a chapter on whether or when you should use Bayesian methodology and like theoretical arguments about that? No, it does not. Does it have a section on Bayesian analysis? No, it does not. Does it mention Bayesian once in the entire book, which is like this thick and has 7 editions or something by now? No. So that just kind of pushes back the question. Obviously, if it's not taught, then people are not going to use it in the social sciences. But why is it not taught? And why are we teaching it now, here, today, this semester? So that's a question we're going to have to come back to as we go along this semester. But, and again, it's going to have multiple parts to it. But I think the biggest part from my perspective is that in order to do Bayesian analysis, you have to be comfortable using probability, manipulating probability, dealing with those sorts of functions. And that is something that people who come from applied statistics departments or statistics departments, they're going to have at least one required class in probability. Whereas people who come through social sciences or a lot of other sciences are going to learn how to do, regression and t-tests and things like that without having a class that spends the majority of its time just going through the nuts and bolts of probability calculations. And without that, doing Bayesian analysis seems like an insurmountable hurdle to get over if you don't have that foundation of probability in place. To me, that's the biggest reason. Now, if we look at the plot over here on the right, this shows the number of Bayesian articles per 1,000 published in the social sciences. And if you look at it, you see the yellow line here for economics, much more prevalent usage of Bayesian analyses in economics as compared to psychology, political science, and sociology. So why might that be? Where are my econ concentrators? 0 econ concentrators? Econ like major in undergrad? Anybody heard of economics? Did you have a thought as to why it's more prevalent in economics than the other social sciences?
I don't have an economics background, just taking a guess. Is it because the discipline is more mathematically inclined than political science and psychology? Inherently?
That's certainly part of it. More articles in econ use quantitative methods than as compared to sociology, for example. Yes?
Has it been that economics as a discipline has kind of moved a little more towards applied and less of sort of those like theoretical models that are based on perfect agents doing, making rational decisions? So would that be maybe a possibility?
Yeah, I think that is part of it. And so, although the empirical models have kind of evolved, you have a lot of theorizing in economics, game theory in economics, where the researcher or the theorist, depending on how you want to define it, assumes that the agents in the model are rational, which is more or less to say that the firms or the people in that model are assumed to be Bayesian. They are updating their beliefs about the world in a Bayesian fashion, because if you sort of don't assume something like that, which is a very strong and dubious assumption, then it's very hard to come up with any sort of predictions from that theoretical model. And so one of the reasons, this is probably an overestimate, but one of the reasons why I think it's more prevalent in economics is accustomed to having theoretical models where the agents in those models, firms, consumers, governments, whatever, are assumed to be acting according to Bayes' rule. But that just pushes back the question, why, if the economic theorists habitually assume the agents in their theoretical model are using Bayes' rule to update their beliefs about the world, why do econometricians who are estimating the parameters of those theoretical models not themselves use Bayesian methods, or at least not very much, more than sociology, but a tiny amount compared to applied statistics? And that's a tough question to answer, a tough question to reconcile. Why economists are willing to make an assumption about how people in firms and whatever behave, but not allow themselves to make those same assumptions when they're analyzing the data from firms and people and So if we look at this, the only social science that has had a rising usage of Bayesian estimation techniques recently is psychology. Why might that be? As compared to pretty much flat in the other social sciences over the past decade plus, a little bit. Yes?
Experiment in psychology?
It's increasing usage of Bayesian stuff in
Because we can conduct experiments in psychology.
yes, although you certainly do see experiments in economics and a little bit in political science as well. So yeah, we can get data, but then the question is, why was there not much usage of Bayesian techniques to analyze those data before, but it's increasing from like 3 to 8 or something articles per year recently. Yes?
Maybe like behavioral economics that falls under psychology, so that's been maybe around since 2005-ish.
Yes,
So could that be a reason for?
could be. What else has been going on in psychology since around 2005-ish?
Replication crisis.
Replication crisis on the part of graduate students, postdocs, assistant professors, etc., fundamentally questioning the replicability, but also just the validity of the empirical results that had been accumulating in psychology, particularly social psychology journals, for decades, which had used non-Bayesian techniques. And as part of the general reappraisal of like everything in social psychology, there was some reappraisal of whether there should be using Bayesian or non-Bayesian estimation. And then why in sociology and political science you have essentially none, and you've always had essentially none. What about sociology or political science data makes them different from econ or psychology data lately in terms of applicability of Bayesian methods? Yes?
I mean, it could be just a lot more qualitative than quantitative, interviews and things like that.
Yeah, it would be better if the denominator were like per 1,000 quantitative articles. That would make it a little bit more clear. But, you know, 0 over anything is pretty much 0. And I don't think we have really a coherent explanation for all the different stuff that's going on in these two charts. So this part I understand. Bayesian was infeasible until 1990, and it became feasible like overnight. So that makes sense. Having so much of a muted response in the social sciences really doesn't, because social science is just applied statistics. Can kind of understand why it's more prevalent in economics, because Bayesian stuff has always been used in theoretical models. Can't really explain why, if it's so widely accepted for theoretical models, why it's so widely opposed for empirical models. I can kind of explain psychology with the recent replication crisis and just rethinking everything, but I don't really know why political science would be any different than psychology or economics with respect to this stuff. And so keep this picture in mind as we go forward, because trying to wrestle with why things are the way they are and what could be done to change them is an important theme for this course. Any other questions about this? All right. So we talked a little bit about the fact that the textbooks that you're using in your other classes don't mention Bayesian analysis at all. And you might say, well, what about the undergraduate level? Do like some of the people around here come in with a background in Bayesian coursework? And the answer to that is no. So one of the authors of one of the books that we're reading this semester has also written a paper cataloging the prevalence or lack thereof of Bayesian coursework at the undergraduate level. Now they were only looking at the United States, so I don't know about the entire world. But my guess is if you went to college at someplace that's not in the United States, there was essentially no Bayesian offerings at all. That's my guess. That might not be strictly true, but it's pretty much true. So let's just say, okay, in order to take a Bayesian class at the undergraduate level, you'd have to go to college in the United States, which many of you didn't, which is, fine. But even if you did, you would have to go to a research university as opposed to a liberal arts college, by and large. Columbia has undergraduate Bayesian course. Hunter College probably doesn't. But okay, so if you go to a research university in the United States, you might have a chance to take a Bayesian course. But those Bayesian courses are almost always in the statistics or the math departments. And very few of you were statistics or math majors as undergraduate. And so those courses would pretty much be closed off for you. So of those 51 places in the United States where you possibly could have taken a Bayesian course at the undergraduate level, only 4 of those require the Bayesian course for a major in statistics. So you could go to a research university in the United States, major in statistics, and still not be required to take the Bayesian class. And if you wanted to take the Bayesian class, the modal number of prerequisite classes to take before you took the Bayesian class is 6. So you would pretty much have to decide when you're a freshman, oh, I want to take the Bayesian class in the statistics department when I'm a junior or a senior, and plan your schedule out accordingly. So obviously, none of you, I assume, have taken has anybody taken an undergraduate class in Bayesian methods? 2 people. So that's a lot who haven't. And so now you're sitting in a graduate class without, for the most part, having the benefit of the undergraduate class or most of the prerequisites. And that's kind of a challenge for nominally 1-year master's programs. Like if there was one course that you could take in the fall that would like get you ready for this, I would say, okay, you're required to take that. But it's not one course. It's like parts of 6 courses, but not even like the whole course. So there's like stuff I could have pointed to you in the stat department or whatever that you could have taken in the fall, but it would just, you would need like 1 month of it. And then the other 2 months would be like wasted, sort of. So we don't do that. We pretty much don't have any sort of formal requirement as to what you have to have taken before you take this. But this class isn't for everybody. It's very difficult to have a class with this sort of workload if you're working full time. It's very difficult if you're part-time. Basically, it means you have to be willing to learn a lot of stuff. It's not really a class to go through to just, get credit and put it on your resume. You really have to invest the time and the effort in learning things that you don't know, including things that ideally you should have known, but there's no way to go back in time and make you choose your undergraduate major differently, etc. Things like that. So what is this class really about? I don't know why it's shaking, but so in my opinion, this class is about how quantitative methods should be used in the social sciences. It applies to science more generally, so we have some people who are outside the QMSS program. We're not going to get that deep into social science, but we will use social science examples even though they're pretty shallow, because the ideas, the reasons why this is applicable to social sciences are just as applicable to science generally. There's a good quote from Bayesian named Don Barry, which says Bayesian statistics is difficult in the sense that thinking is difficult. So this is a class about how to think quantitatively when doing science, particularly social science. So it's essentially a combination of a full semester course of probability at the master's level, even though you probably haven't taken a semester at the undergraduate level, a substantial part of the theory and methodology that was not even raised, let alone answered, in the required course for QMSS students on theory and methodology. So, like I said, you think a course called Theory and Methodology would have some theoretical arguments as to what methods you should use. But they don't even touch this question of should you be using Bayesian methods or non-Bayesian methods when doing social science. We'll be learning some new R packages, not that many, but some, that utilize the external project Stan in order to put 1 and 2 into practice. And also, unlearning a lot of what you think you learned, but you didn't actually learn that well in many of your other classes, whether at Columbia or at somewhere else. And that's a lot for one semester. And you might say, well, could we just do like half of that? The difficulty with being, more limited is that there's no like 5066. There's no like class that follows this in the QMSS. So if you want to become somewhat able to do Bayesian analyses, you've got to get from pretty much 0 to that level in one jump or one semester worth of a jump. Because there's no more there's no extension of this at the master's level for you to take. So we might say, okay, well, let's just do like part of this. That would leave you hanging. You maybe would feel a little bit more comfortable with it, but you would not have yet reached the level where you can say, like, I can do a Bayesian analysis. And, if you can't get there, then what's the point of getting here? So we've got to get all the way. Now, or at least all the way where you can do some basic stuff with Bayesian analysis. So I mentioned Stan. And when I mention Stan, I have to also mention that this being Columbia and me being employed by Columbia and Columbia receiving several research grants over the years to develop Stan. So Stan, the project, originated at Columbia. It's now pretty much a worldwide thing. But the fact that I also use Stan outside of Columbia, actually with a former QMSS student, means that the Columbia University policy requires disclosure of that fact under a variety of circumstances, all of which apply here. Doesn't mean you can't do those things that I do using Stan, but it does mean that I have to tell you and everyone on YouTube about that. But while we're disclosing stuff, I should also disclose that Stan was featured in the plot of Billions, season 3.
You ever done Math Meetup?
Is that what this is?
Yeah, it's a chance for like-minded users of open source programming language R and data analysis tools like Python, Julia, C++, and Stan to get together and exchange ideas.
It sounds stimulating.
It is.
Indeed it is. Now Showtime, not being an employee of Columbia University, can write stuff like this into its script without disclosing these sorts of things. But anyway, so if you want to learn more about Stan, I think you could probably stream that. Okay, so we're going to use R through RStudio, and if you haven't used R before, this is going to get difficult because we don't really teach the basics of R, presuming that most of QMS's students have either had a class that used R last semester or previous semester, or have at least, you know, been a little bit familiar with it. So certainly with all the other stuff that we're trying to accomplish this semester, we don't really teach the basics of R. Now, the R that we use is not at a very advanced level. You basically just need to be like a little bit familiar with R, and you'll be able to do it this semester. But many of the things that we use don't have equivalent functionality in Python or anything like that. With homeworks, we'll be using the Quarto format, which is the successor of R Markdown. We'll demonstrate how to do that in the right format for turning in your homeworks, etc. But if you know a little bit about the R language, you'll probably be okay. And if you don't, then that is going to be a pretty serious obstacle to staying in the class. Now, Stan is another programming language. And we're not going to learn the Stan language directly. Its algorithms and whatnot can be accessed from R and Python and a bunch of Julia and a bunch of other things. And you may prefer to use those for Bayesian inference after the course is finished. But you sort of have to learn on yourself the Stan language in order to then do those. R has by far the most intermediate layers to let people use Stan without directly looking at Stan under the hood, so to speak. And so that's why we're going to use R. And if you can at least read this R function, you might be okay. So this function implements what's known as the Collatz conjecture, which is that this function terminates for all positive integers. And so we have a requirement that x has to be a single positive integer. We check all that, and then we go into a while loop while x is not 1. If x is an even integer, divide by 2. If x is an odd integer, multiply by 3 and add 1. And the Collatz conjecture is that for every positive integer, this will terminate. It'll jump out of the while loop and return true because x gets to 1. And you might say, who cares? Well, Collatz cared. A lot of other people cared, but they were mathematicians. And the way in which mathematicians think is that if there's a single counterexample, if there is any positive integer for which this function doesn't terminate, it either goes off to infinity or it goes into like a cycle that doesn't hit 1, then the entire Collatz conjecture would be falsified. If there's one counterexample to a proposition like this, then the proposition is false. And only if it's true for every single positive integer, only if we can prove that it's true for every positive integer, will mathematicians accept that this is true. And mathematicians have no idea whether this is true or not. It has been verified that this holds for all positive integers up to like 1 billion squared. But mathematicians are unwilling to say from the fact it holds from all positive integers up to like 1 billion squared that it is true in general, no exceptions. And if anybody could come up with like one exception where it's not true to falsify the whole thing, they would win like huge prizes and get tenure in math departments and things like that. And so that's how theoretical math works. All right, and part of philosophy and some stuff like that. It is a truly awful way to think about social science, Because for everything that is true in social science, there's an exception. Even the exceptions have exceptions. So if we had this standard, if there's one counterexample, then the whole thing is false. If we applied that to social science, nothing would be true or useful or scientifically valid. And so this is just like a non-starter, really, for a way to approach social science, and yet it kind of crops up. And to maybe put this in a little bit more of a general terms, this is what's known as Aristotelian or propositional logic, where Aristotle was ostensibly the first person to argue deductively like this. And it's said in one of Aristotle's books, well, every human being is an animal. Socrates, who's the sort of generic example in all of Greek philosophy, is a human being. Ergo, Socrates is an animal. And you might say, like, why is Aristotle considered such a genius? For coming up with something that seems like basically a tautology, but, you know, one step at a time. But this sort of reasoning is useless in the social sciences, because science by their nature is inductive rather than deductive. The closest thing that I can come up with that mirrors this pattern is democratic peace, which is the dumbest area of political science, but it goes like this. Major premise: democratic countries won't fight a war against each other. Minor premise: Australia and Canada, or whatever two democracies you want to pick, are democracies. Ergo, Australia will not fight Canada in a war. Now, the fact that Australia and Canada have never fought a war previously doesn't really establish that this whole thing is true. Indeed, whether it's true or not depends on how you operationalize country, and how you operationalize democracy, and how you operationalize war. And for that reason, the literature on democratic peace de-evolved rapidly into searching, well, has there ever been a war between two democratic countries? Instead of going in a much more useful direction, which is to observe that like well over 99% of wars have involved at least one autocratic country, and saying democratic countries are much less likely to fight wars against each other. Why is that? That would be a reasonable political science research agenda. But instead, it's sort of de-evolved into, was the Falklands War a counterexample to this? Depends on whether you consider Argentina to have been a democracy at the time, which is like stuff like that. Instead of focusing on the big picture, almost all wars involve one autocratic country. Why? Explain that. Okay. So what social science usually works is this like weaker form of the Aristotle thing. Maybe something like this. The party of the United States president tends to lose congressional seats in midterm elections. Joe Biden is a Democrat. We know that for sure, but you're not even required to be absolutely sure about the minor premise. Ergo, Democrats will probably lose some congressional seats in the 2022 midterm elections. So, is that true? Is that sound reasoning? Do you buy this? Like 2022 was last year. Did this happen?
Yes.
Yes. Lost seats in the House. Gained one in the Senate. This doesn't really specify which chamber of Congress the theory is, applied to. So, kind of yes, kind of no. And then you have this word some. So, yes, it did lose some seats in the House. But if you read almost anything, you'll see they lost fewer seats than what people thought based on historical trends and whatnot. So now if we're talking about like degree of losing how many seats, like a lot or a little, is it enough to flip control from, the Democrats controlling to the Republicans controlling, those sorts of things? Those are all questions of degree. And even if you say, well, 2022 was sort of an exception from, recent history, that doesn't really mean one is false. It's just there's more qualifications to it. And so if you look at something empirical like this, well, 1 and 3 are not guaranteed. It's not like ergo Socrates is the animal level of certainty. But 3 seems plausible to some degree to the extent that you accept both 1 and 2. And the Bayesian approach is a school of thought that uses probability to describe your degree of belief, to quantify your uncertainty about your belief, as to whether a proposition is true or not. And so this probably is an important word here. And it's why we have to introduce probability into our analyses. And that's why without having like a previous class in probability, it seems like a steep learning curve to be able to make these sorts of assessments, which are germane to political science and really all of social science. Stuff like this. Something tends to be the case that is applicable, ergo some conclusion, but the conclusion is not guaranteed because the premises are merely probably true, likely true, they tend to be true, they're mostly true, rather than something that's absolutely true, like Socrates is a human, or something like that. But this is where it gets interesting from a social science perspective. Not like, is Socrates an animal? Was Socrates an animal? Things like that. Questions so far? Alrighty. And for this and a lot of other things, we can actually have futures markets over various events, such as who will control Congress. And so the idea of these is you can pay some amount of money, which is given in cents on the vertical axis, and you essentially get a futures contract that pays you $1 if the event transpires. And there's 5 events here, most notably in green. Republicans control the House, Democrats control the Senate in the 2022 election. Republicans control the House, Republicans control the Senate in the 2022 election. And the other possibilities, including a tie in the Senate or whatnot. And so as you can see, this is the wrong year. I meant to get a more updated picture. Anyway, this goes back to 2021. And you can see the probability in these markets of the Republican controlling the House and Senate was increasing. And at this time last year, so this is 22nd of January in 2022, the markets were pricing like an 80% probability of Republicans controlling both the House and the Senate when the 2022 elections actually happened in November and December with the runoffs. So I'll put the updated picture here, but you can see the probability went up and then it like went down kind of over last summer, and then it went up again in October and like early November. It actually got to about 80% probability again. Republicans would control both the House and the Senate, but as the election results started going in, it became quickly clear that Democrats had a good chance to hold at least the Senate. And so these lines, drifted around as the assessed market probability of these things happens changed as a result of new information coming in, new polls, and inflation going up, and then like not up as much, and stuff like that. And so one way to sort of see what this class is doing is that the Bayesian approach prescribes how these beliefs should change as a result of new information coming in. Now, what markets actually do an efficient market hypothesis, and whether they're actually behaving like this, no. But the Bayesian framework gives a way of assessing how beliefs about these future events or unknowns, they could be microscopic or future or unobservable, any sort of unknown changes, should change as a result of new information coming in. And that's what we're going to learn how to do. And so, like I said, the reason why we introduce probability up front and use it so much is really to quantify uncertainty in our scientific analyses. And there are a variety of sources of uncertainty that we potentially have to deal with, or really always have to deal with. One, uncertainty about parameters in models. So that could take the example of a regression coefficient. That's one sort of model, linear model. It has unknown intercept, unknown slope, unknown error variance, things like that. And so we're uncertain as to what those parameters are, even assuming a linear model is correct. But a linear model might not be correct, or a linear model might be correct, but only if you condition on, this or that predictor. If you omit something, then it's not so correct anymore. So we have uncertainty as to which model is best in a particular situation. Then, assuming we've established which model is best, and assuming we've established what the parameters are, we have uncertainty as to what to do with the output. So, after you've obtained your estimates, how would you proceed with the implications of that model? There's, certainly a lot of gray areas as to what you could do with that. Fourth, which is what is not talked about very much, uncertainty as to whether the software works as intended. And this is something that you should not take for granted. And it's talked about a little bit in the McElreath reading for today, and we're going to read most of the rest of that book. Over the course of the semester is that when you're, taking classes, you can definitely fall into a false sense of security that like ordinary least squares is going to work. But that's one, because it's like a cooked textbook example and a very simple estimator and stuff like that. But two, it is, if it's being applied, it's being applied in situations where it's had a lot of attempts. And we're pretty familiar with how the estimator behaves when subjected to these past data, in a variety of fields and whatnot. But as McElreath emphasizes, when you're doing science, particularly scientific research, kind of by its very nature, you're applying an estimator to new data, particularly when you're doing cutting edge stuff. And so we don't have this like decades of experience with how well an estimator performs when it's being applied to new data in this new area where it hasn't been applied before because the data didn't exist before or something like that. And particularly in those situations, not so much with least squares because it has a closed form solution, but with a lot of the other estimators, the software can not work as intended and not tell you it's not working as intended. Because the software doesn't have the ability to sort of see itself from above. It just sort of does what it's told. And so you as the researcher need to provide the skepticism as to whether the software is working as intended. And with this sort of off-the-shelf stuff, Mick Elry says it's brittle and fragile. And its ability to not mess up when confronted with new situations that are a little bit different from the situations the software was developed for. And that's why you need a general framework for analysis, the Bayesian one obviously, but also software that allows you to customize the analysis and to be able to tell from the software output if the software worked as intended. And then uncertainty as to whether the model holds with other data, be that future data or like a slightly different subgroup of the population, things like that. And Bayesian's, refresh. Anyway, Bayesians use probability to describe their uncertainty about 1 and 2 and 5. And along with a slightly related branch, very closely related branch, called decision theory, prescribes how to make decisions as to what to do with the model output. Now, we haven't really integrated 4 into the rest of this, but the STAN software does as much as we can and much more than other software to mitigate 4 and to provide warnings when it's not working as intended. And other forms of inference, other software, etc., is going to make different choices and different trade-offs as to how they wrestle with these sources of uncertainty in doing those analyses. And you know, those trade-offs are not necessarily the ones that you would make if you want to be doing scientific research, cutting-edge scientific research. So let's try to go through an example of Bayesian inference. Been talking a lot here. What do you believe is the average age of Columbia graduate students? Anybody else?
26.
26. All right. So none of you, or neither of you two, but neither anybody else, are completely sure what the average age. You have a pretty good idea, but you're not absolutely sure. And if we're talking about average age, it's probably not even an integer. But somewhere 25, 26 seems like it would be reasonable. Okay. Can you describe your beliefs about the average age of Columbia students using a normal distribution, otherwise known as a Gaussian distribution? So in terms of, you know, the mean and the variance, or let's say the standard deviation or something like that, of a normal distribution, how would you describe your beliefs about what the average age of a Columbia graduate student is?
I guess if we're going to say 26 years old is the average, probably 68% fall between like 30 and 22, where the standard deviation would be 1.
Okay, so 26 with a standard deviation of 4.
Yeah, 4.
And you're saying, the reason why you're saying that is you think about 2/3 of Columbia graduate students are between 22 and 30, with an average of 26. Okay. That is a coherent set of beliefs. So if you describe your beliefs in terms of a probability distribution, like the Gaussian, that's sort of the like statistician equivalent of making a complete sentence. So you don't necessarily have to agree, But if someone says normal 26 with a standard deviation of 4, I know what you're saying. You like finished your thought. Now, does anybody take issue with that distribution? Yes?
I'd probably say it's more of a skewed distribution, with a long tail on the right going into the higher ages and kind of a sharp drop, probably around 22.
Yeah, so some question as to whether Gaussian distribution for the average would be appropriate. And yeah, because you sort of have to have a minimum age, basically, more or less, to have graduated college and then be in graduate school. So you could have a little bit of that. But do you think 2/3 of Columbia graduate students are between 22 and 30, and thus 1/3 are greater than 30, pretty much, because probably none are really less than 22? You think it's 1/3? More? Less?
A little less.
A little bit less. So maybe if we were going to insist on using a Gaussian distribution, we might want to have a smaller standard deviation, like 3 instead of 4, or something like that, to put more probability on people being in their 20s and less in their 30s or older, although there are some certainly there. Okay, so normal 26, 3, 4, 2, anywhere in there would have been reasonable. And we're not going to get too much details the first day, but what the Bayesian approach does is it transforms the normal distribution that you said, 26 and 3, whatever, of beliefs into a different, but in this case also basically normal, probability distribution of beliefs after observing the data, such as the ages of the end students in this class. So seeing the data allows you to update your beliefs to change the probability distribution you started with into a new probability distribution that tends to be more accurate because you've observed data that you hadn't observed previously. That's the essence of the Bayesian approach, transforming one probability distribution into a better probability distribution by utilizing data. But that's really different from other forms of inference that are used in the sciences, social sciences. Randomization inference, frequentist inference, supervised learning, that don't yield probability distributions. They, for the most part, yield point estimates. And so kind of the advantage of the Bayesian approach is it's much richer to have your answer be a probability distribution, which quantifies your uncertainty, than it is to have a point like 25.3. That can't be exactly right, but we don't know how wrong it is from the output of that. So let's briefly mention some of these other approaches to inference. So this is the audience participation aspect of it. So form pairs with your neighbors, and exactly one person in each pair should either execute this in R, or you can just flip a coin. Same thing. So in R, you would take a sample from the set V and U of size 1, draw that person. That person will be considered the treated person. The other person will be considered the control person. And the quantity that we want to compute is the difference in age between the treated person and the control person, which may be negative or 0. But it should be an integer. Okay, so pairs. If you have R, open it up, execute this. If you don't have R, flip a coin or something else.
Do you have so annoying, but okay, no worries. Oh, I see.
All right. We got it? All right. Got some data. Before we get into it, right. So before we get into the individual data points, what do you think is the average difference between the age of the treated person and the control person in this classroom? 0. And that is because the result of this randomization process doesn't make anybody any older or younger. I mean, if we could, we would, but you all are already pretty young. So this treatment has no effect because age is something that was determined in the past, decades ago, for you all. So the average difference should be 0. But how much do you think this estimate of the average difference could depart from 0 if there are, let's say, 44 people in this class, which is ostensibly the number of chairs we have? Let's call it 44. So the average isn't going to be exactly 0. How much do you think would be like plausible deviations from 0 if this treatment effect is truly 0, which it is? So do you think it's plausible to get an average difference of like 1 or -1 or something like that among the 44? Okay. So everybody all at once shout out, one person from each pair, shout out the difference in age between treated and control person. Ready? 1, 2, 3. Okay. Everybody was saying a bunch of different numbers. 1, because we have randomness here and who got to be treated and who got to be controlled. There's also some randomness in terms of who sat next to who and whatever and things like that. So we're not going to do it again. But if we did do it again, you could imagine the answers being different because you'd be paired up with different people, and also who gets to be treatment and control would change just randomly. And there are that many ways to form pairs among 42 students, which is how many I thought were going to be here today. And that defines like a probability distribution of average differences. It should be centered on 0, but it's going to randomly differ from 0. How much? And that's where Fisher's idea of a p-value, where's my, whoops, need to reload this. One second. This is where Fisher's idea of a p-value comes in experimental research. Where is it? Okay, did the Bayesian one, did the uncertainty. Okay, so there's a whole bunch of different ways in which the data could be paired up. And if you take those differences and divide them by their standard error, you should get a distribution over that like 5 bajillion ways. in which we could have done the pairs. Between treated and control, it would look like this. So this is going to have an area of 1 underneath the black curve. And as you might have learned in some of your other classes, if the value that you observe, so the amount of area to the outside of the red vertical lines, which are at 1.96 and negative 1.96, this is 2.5% in here and 2.5% in there. And so the way in which design or randomized inference works is you sort of look at the estimate that you obtain and see, well, what proportion of the possible ways that we could have randomized into treatment and control would yield an estimate that is bigger in magnitude than the estimate we actually obtain. And the convention is that if your estimate that you obtain is sufficiently far out into the tail of this distribution, the p-value will be low. It would reject the null hypothesis of no treatment effect when doing something like that. But in this case, there is no treatment effect, and so there's a 95% chance that we would get an estimate somewhere in here among the 42 or whatever of you all. And that Fisher published this way of doing things in the 1920s, and it was very influential, still influential today. But one of the most astounding, well, it's not astounding to me, but it may have been astounding to you. It certainly would have been astounding to a lot of people in the social sciences. On page 10 of the reading for today, McElreath says, the greatest obstacle that I encounter among students and colleagues. So he is kind of an evolutionary anthropology, biology, something that's kind of social science adjacent, but I think the same thing would be true in social sciences like economics and political science and psychology, etc. Anyway, the greatest obstacle that he encounters among his students and colleagues is the tacit belief that the proper objective of statistical inference is to test null hypotheses. And he talks about how this is sort of a distortion of the view by a philosopher of science named Karl Popper. It's not something that Popper really said. But the reason why McElreath thinks that this is the biggest obstacle, that it's not really correct, that the proper objective of statistical inference is to test null hypotheses, is for two primary reasons. One, hypotheses are not models. So any model of any phenomenon in the social science is going to be a bundle of different assumptions and different hypotheses that go into it. There's no such thing as like a model that just isolates the one hypothesis entailed by it. And so to the extent that some model is inconsistent to a greater or lesser degree with the observed data, we don't know which assumption of the model is failing, whether it's the one that we're particularly interested in or another assumption that kind of came along for the ride, like linearity or something that wasn't, entailed by the model. But even if we didn't have that problem, the fact that there is measurement error in every branch of science, but there's a lot of measurement error in social sciences and sort of social science adjacent things like evolutionary biology, measurement error prevents deductive falsification. So even if you could sort of do some Aristotle thing to deduce a conclusion, if you don't measure the variables perfectly, then the conclusion is not going to be perfectly reflected in the data and the model that you're fitting to the imperfect data. And measurement error inclusive of missing data is so prevalent in the social sciences that you really cannot proceed in this purely deductive way of trying to falsify a null hypothesis. And kind of to summarize that, but maybe not using exactly Mikhail Breith's words, empirical science depends on what a treatment effect is, or whatever parameter you're trying to estimate, not what it isn't, which is like the hypothesized null value, often 0. So to say, oh, well, this treatment effect is not 0, is a meaningless conclusion from a scientific perspective. You've literally excluded one real number from the entire number line, which has an infinite number of points. So you can exclude 1 point, you still have an infinite number of points that it could be. So to say, like, you know, the treatment effect of the COVID vaccines is not 0. What do you do with that? Is it beneficial? Is it detrimental? Those are both not 0. Is it beneficial enough to be worth spending billions of dollars to get everybody, you know, vaccinated? You have to say what the treatment effect is, not what it isn't. But in saying what it is, you've got to be honest about your uncertainty in your estimates that you make. So that was an example of randomization inference, where probability is needed in a very limited capacity, but it is needed due to overt randomization of treatment and control status on the part of the researcher. And so probability is needed due to the randomness induced by flipping coins or whatever it is to put some people into treatment and some people into control. That was random, the sample business or flipping the coins, however you decided it. And so any function of that randomness is also going to be a random variable. And thus, we need probability and probability distributions to describe the consequences of overt acts of randomization on the part of a researcher. So probability is important, but it's very, like, has a very narrow role due to randomization induced by a randomness induced by randomizing units, some into treatment, some into control. Now, the same guy, Fisher, also in the 1920s, more or less came up with, or certainly popularized, another approach that is not limited to experiments, known as frequentist inference, which is a little bit different, but has a lot of the same ideas. So we said earlier the average age of Columbia graduate students, you were saying, you know, should be 25, 26. Let's call it 26. Let's say that's our hypothesized value. Now, if we presume that each row in the class here is a sample from the population of graduate students, start on the left over here, and then add your ages going rightwards, and the person all the way on the right of the row divides by the number of people in the row in order to get the average age of each row here, which we're going to consider to be a sample. So start on the left, go to the right. You can use R if you want to.
So yeah, we actually got the 76. I was gonna say, wow. She thought you said you were 76. This is wrong. Okay, what's that? One more time. 23, 22, 24.
Let's go.
All right.
25.
Okay. We can do some arithmetic. All right. So let's record this. All right. So row 1. What did you get? 26.4. Okay. What was the sum?
132.
So 135 over 6.
132.
132
Over 5.
over 5. Close enough. Okay. Row 2.
Yeah, 187 over 7.
Oh, okay, you're row 3. Okay, row 2.
149 over
Okay, row 4.
209 over 3.
209 over 8. Okay, row 5.
156 over 7.
And row 6. Whatever.
153 over 6.
153 over 6. Okay. So those are different numbers due to, one, we have pretty small samples here. But there's randomness as to who sat in which row and whatnot. Now there's some question as to whether the graduate students here are a random sample of graduate students at Columbia. But let's just put that part aside. It's important, but let's put it aside for today. Now, the essence of the frequentist approach hinges on what's known as the central limit theorem, which assures us that the distribution of averages over all ways to randomly sample in graduate students from the population of Columbia is asymptotically normally distributed around the true average age of Columbia students. So this is just like 6 ways in which we could draw a small sample of graduate students from Columbia. But if you fix n to be 10 or 100 or whatever it may be, and think about all possible ways to sample n graduate students from Columbia, the distribution of the age and the sample is normally distributed with expectation, the true population average age in Columbia. And this idea of random samples and functions of data from random samples is really what's driving the frequentist approach to inference. But although we can say what the numbers are in a sample, we can't be sure as to what the numbers are in the population from any finite sample of size n. And so frequentist inference proceeds with this sort of quasi-deduction sort of thing. And the same is sort of true for randomization inference, that if the null hypothesis is true, then the estimator, perhaps with some standardization, will be greater than 1.96 in magnitude in 5% of possible samples of size n from whatever population you're talking about. So that's like the major premise. The minor premise, in any particular case, you might get a p-value based on doing some computation from the sample that you have is being less than 0.05. Ergo, the null hypothesis is falsified. So that's the procedure, but that doesn't even really make sense, because even when the null hypothesis is true, the estimate is going to be greater than 1.96 in magnitude 5% of the time. So the fact that you get 0.04 or whatever, it's not super inconsistent with the major premise. Now, it's not often going to happen if the major premise is true, that you get p-values smaller than 0.05. But 2% of the time when the null hypothesis is true, you're going to get a p-value of 0.02 or less. So it doesn't really seem like it makes sense to absolutely reject the null hypothesis when it's like possibly true, even when that probability of it observing estimate so large is small. But putting that aside, what scientific purpose really gets accomplished by deciding that the null hypothesis is not literally true? So if you say 26 and it's actually 26.1, the null hypothesis is false in the sense that 26.1 is a different number than 26. But if you have enough data, you'd be able to reject that. But again, what scientific purpose is really achieved by saying, oh, it's not 26? Particularly when the evidence from the data that you have suggests it's very close to 26. Probably for any practical purpose, 26.1 is the same as 26. But that's not the way it works in this sort of trying to be deductive framework in a situation that does not call for deduction. But this framework is used all the time in the social sciences and other sciences for not very good reasons. So the next way, so it might seem a little bit weird to bring up all these sorts of contrasts between the Bayesian approach and frequentist or randomized inference approaches, which were popularized by Fisher in the 1920s. And even like later in Fisher's career, he wasn't even really talking about this stuff all that much, and he died in like the 1960s or whatever. So why are we still talking about this? And moreover, why are we talking about this in the social sciences when Fisher himself was not a social scientist? He was a biostatistician. Social science as we know it today didn't even exist during the 1920s when Fisher was sort of starting his, or at the peak of his career, let's say. So one reason why we're still talking about it is because it's still being used. If you read any sort of journal in the social sciences, you'll see frequentist inference and sometimes design-based inference being applied all the time. But also increasingly, you'll see the use of supervised learning, which if you go back to the plot that I showed on the first slide there, it didn't have anything to do with supervised learning, but if you just guess what the curve would look like over the past 20 years or so in terms of the usage of supervised learning in the social sciences, or maybe also in statistics journals, it also would have been very little, at least up through sometime in the 1990s. And then I would say really about 2000, it started to take off, and it probably is increasing at an increasing rate. So you're much more likely to see supervised learning stuff being done in the social sciences than you are to see Bayesian stuff. So maybe we should be asking the question, and we will ask the question, like, why should Bayesian methods be preferred, or when are they not preferred, etc. So what is supervised learning all about? Supervised learning, it's like frequentist estimation in the sense it focuses on point estimates, but without the null hypothesis testing. So no p-values, no confidence intervals, no rejected null hypothesis, no type 2 error, none of that. We just estimate, and because we're using the estimate for a different goal, namely to predict future outcomes, that allows us to tweak the estimator a little bit in terms of using penalty functions and things like that in order to get better predictions of future outcomes than what frequent estimators yield. And it's been fairly well established that frequent estimators yield pretty poor predictions of the future. And it may kind of come as a surprise, but predicting the future was not Fisher's goal in the early frequentists, etc. They were really interested in estimating parameters, estimating treatment effects, making scientific conclusions about unobservable things like parameters and stuff like that, rather than predictions of future observables. So using maximum likelihood and least squares and whatnot for the purpose of prediction, when that really wasn't their original motivation for developing these sort of estimators, may come as no real surprise that you can do better by using some sort of a penalized estimator, etc., in a supervised learning context. So let's suppose in our example that the back row there is testing data, and the other rows in the class are training data. So this is a little bit like k-fold cross-validation sort of deal. And so we got somebody with a phone add up all these numbers. 132, 149, 187, 209, and 156. So all the numerators there. Okay, I'll take your word for it. And then divide by 32.
26.03.
26.03. So the average age among people in the first, whatever number of rows here, 26.03. And we're going to use that as a prediction for each of the individuals in the back row, which is going to constitute our testing data. And so for each person, come up in the back row, come up the difference between your age and 26.03. Just like think about what that is, or average it up among the back row. What do we got?
The difference ended up for all of us is 23.
Okay. And then there's 6 of you?
Yeah, so 3.8.
Right. Okay. So this is not a perfect prediction, but it's a plausible way of making prediction for held out data. This is a very simple way of dealing with the training data. Certainly you can do much more complicated things with like convoluted neural networks and stuff like that. But anyway, kind of the purpose of supervised learning is prediction of future observables. And what you want to do with the training data is apply a lot of plausible techniques to try to figure out what predicts best in the testing data in terms of what has the lowest average or absolute whatever residual when extrapolating into the testing data. So a lot of you are familiar with that idea. It didn't involve any null hypothesis or any p-value confidence interval. None of these concepts from statistics were needed in order to use the training data to yield us a prediction for each of the people's ages in the testing data. And we could have done that with different k-faults and all kinds of additional complications, but that's the essence of it. All right? Now, what you'll see a lot of the time is that the testing data is a randomly selected subset of the total data. But supervised learning usually does not really consider the implications of the randomization into training and testing. It's not that hard to do, and you'll see it be done sometimes. It would be very analogous to randomization inference, where we sort of fix the classroom and then randomly assign some people to treatment and control and then consider the probabilistic implications of that randomization. If we consider like training to be treated and testing to be control, and we randomly take a subset to be training and the other subset to be testing, and then we do something that's a function of the data, well, that randomization into training and testing, everything that's a function of that is going to be a random variable. And we could analyze it with the tools of probability in much the same way that Fisher analyzed experiments with randomization into treatment control, even though this supervised learning stuff is usually applied to observational data rather than experimental data. But supervised learning really de-emphasizes probability distributions, particularly at the sort of introductory level. There's some stuff that sort of has probability lurking in the background, and maybe as you get into more advanced stuff, that kind of comes into the foreground a little bit more. But there's certainly a view that probability should not be an obstacle to getting people involved in doing supervised learning. Like, you should be able to do lasso or whatever it is without having to know probability in order to do it. So probability is very much optional for supervised learning, in part because they don't want the conclusions to hinge on particular assumptions or whatever about probability distributions. But more than that, they want people who don't know anything or much about probability to be able to do at least basic supervised learning stuff, where if there is probability, it's in the background, like somewhere in the layers of your convoluted adversarial neural network thing. Like maybe there's some probability there, but you as the person don't really have to engage with that in order to like feed your picture of a cat into it and like have the computer classify this as like a cat or not a cat. And the fact that particularly when you're doing classification, you get this like, yes, it's a cat, or no, it's not a cat answer, as opposed to something like, there's a 97% chance that this picture is a cat. And, you know, Google and whatnot, they've gotten pretty good at distinguishing pictures of cats from other pictures. But that doesn't really seem to rise to the level of a scientific conclusion. You've just sort of taught a computer to recognize a cat or compose a sonnet about a cat or something, write a song about a cat, those sorts of deals. That, you know, is different from saying, does this intervention improve students' achievements in high school or something like that, which is it's a different level of thinking that's what's really going on with these supervised learning things. So to try to put these four different, and there's others, but these are the main four, paradigms of quantitative methods into one table here, those being randomization / design-based inference, frequentist inference, supervised learning, and Bayesian into one table. I think it's helpful to think like what is the role of probability in each of those, and what is considered fixed and what is considered random. So whatever is not random is being held fixed in these things. So the randomization / design-based approach fixes the data. In particular, it fixes the outcome of all n observations. So you observe what it was. But what was random was the assignment to treatment and control. And so you then evaluate over all possible ways to assign treatment and control, what would, some function of the data, some of which are going to be treated, other which are going to be controlled. And you come up with your estimator, and you're averaging over all these hypothetical ways that you could have put half the people into treatment and control or whatever. And the conclusion that you come up with in design-based inference is, what's the p-value for a null hypothesis that the average treatment effect is 0. And you can sort of proceed like that. The frequentist inference, although it involves the same view of probability, is actually pretty different. What we're fixing here is the population, including the parameters, theta, in the population, and the number of observations we're going to randomly sample from that population. So what's random is who is included in the sample and who is excluded from the sample. Like if we're going to do a poll of size n equal 1,000 and ask you, like, do you support, Biden or Trump or, whatever, stuff like that, 1,000 people are randomly going to get included and millions of people are randomly going to get excluded. But if we take some function of the sample, then the fact that we've induced this randomization by randomly sampling from the population is going to precipitate random variables that we can analyze with confidence intervals and stuff like that in order to do hypothesis testing. And that's the sort of stuff that was certainly covered well in the data analysis class last semester. With supervised learning, again, it doesn't really hinge on it being a random sample, or it can be observational, all sorts of things like that. So we're really fixing the outcome, but we're randomly choosing a subset that's going to be training, and the complementary subset is going to be testing. And that's the sort of randomization. Like I said, it would be rather easy to analyze in much the same way that we do with experiments, but in practice, supervised learning people don't do it that often because they don't really want to emphasize probability. But what's averaged over is the loss or the residual in the testing data when you apply some estimation method to the training data and then use that to make predictions into the testing data. And the conclusion that comes out of a supervised learning analysis is like this one procedure out of the 20 or something that I've tried predicts best in the testing data. So I'm going to use it in order to make predictions about the future. And then where does Bayesian come into all that? Again, it's going to fix the data. So it does not assume that it's a random sample or anything like that. But what's random, or what's treated as a random variable, is you as the researcher's prior beliefs about the parameters theta that were responsible for generating the data. And then when you use this data, it transforms the prior probability distribution representing your beliefs into posterior beliefs, updated beliefs about the parameters theta. And the way in which this gets estimated, like I said, with modern Bayesian inference, which is tremendously general, you get a whole bunch of random draws on your computer from the conditional probability distribution representing your beliefs about the parameters given the data and what you believed about the parameters before you saw the data. And you can use that along with decision theory to make a decision or an action that maximizes your expected utility, taking expectations over this posterior distribution of beliefs that you obtained by conditioning on the data that you observe, which modifies your distribution of beliefs about the parameters that you had coming in. And so if you sort of plug your utility function into that, you can come up with a decision that maximizes expected utility. And this gets back to the connection with economics, because maximizing expected utility is a very common thing that all like economist graduate students learn how to do. But then the question is, why don't they avail themselves of that possibility when doing econometrics? Because they could, and we'll certainly learn how over the course of this semester. So just to put it in one sentence, these four, and there's others, but like I said, these are the main four, for doing quantitative methodology, they're very different, but they're also incompatible with each other as to like what is being considered random and what is considered being fixed, and what the goals are, the conclusions that you reach, and they're incompatible with each other. So what this class is about is really why, particularly in the social sciences, you should prefer to use the Bayesian approach. It produces a much richer answer than these sort of things, which at best produce point estimates. We now have distributional estimates, and have a much more rigorous justification for taking a decision or action as a result of the conclusions that we make in the study. So that's kind of what we're going to do this semester in a nutshell. And so the last thing that I want to do is talk about the syllabus a little bit. Okay, sorry about that. I had to log in. If you haven't seen it already, the syllabus is on the course website, which should be accessible to everybody. Since I uploaded the last version of the syllabus, we've actually gotten a TA. His name is Burki. He's back there. So we'll have recitation sessions at a time to be determined a little bit later in the semester. Those will be over Zoom, so if you can't attend those in person or you need to watch it afterwards, you can do that. We talked a good bit about the course and the prerequisites or lack thereof. Basically, if you're a QMSS student, you're presumed to have enough background to be able to learn this, but other non-QMSS students with similar backgrounds are certainly welcome to participate in the class. Grading, for people who are taking it for a grade, it'll be based 1/6 on class participation, which is going to be assessed online. I'll talk about that in a second. 1/2 for the homework assignments collectively. We'll probably have about 5 homework assignments, so roughly one every 2 weeks. And also 1/6 on the midterm, which will be right before spring break, and 1/6 on the final exam, which will be during exam period in May. If you take it pass-fail, the same weights, but you don't get a letter grade, you just get like pass. You can have R credit, like official auditing, in which case you don't take the final exam, and all the weights be renormalized relative to that. And so with regard to class participation, hopefully you've seen on the course website, there's a link to this thing called Ed Discussion, which if you haven't used it before, is basically an online forum where you can ask questions and other people can see your questions and respond with answers and follow-up questions and whatnot. Ed Discussion is particularly good because you can include R code snippets and they get executed on the Ed Discussion cloud or whatever. Anyway, what is good class participation is to ask one question or to correctly answer another student's question on the reading for each week. So far, none of you have asked any questions or provided any answers. about the reading for today, so you're already behind. But like I say, if you average, one good question or one good answer to a good question per week, that would be considered good class participation because of the nature of the class. Because we're covering so much so quickly, and we're doing it at such a general level. Like, what methodology, what quantitative methodology should be used in the social sciences, and why should it be Bayesian, and how does this relate to the other classes that you're taking that are not using Bayesian methods and things like that. There really ought to be much more than an average of one question per person per week. There ought to be like one question per hour, because there's so many things that could be asked about, including, how does this pertain to other weeks. Once we have homework, there's obviously going to be a lot of questions about the homeworks and whatnot. You can make a private thread, in which case only me and the TA will be able to respond to it, so you don't give your answers away to anyone else who's still working on it. I mentioned a couple of the books already. You don't need to buy any books. All of these are available online, but you could buy if you want to. And we did the chapter 1 of these books for today, and we'll pick it up next week on Thursday, getting directly into probability and really emphasize probability for most of the next month or so. But anyway, so take a look at that if you haven't already, and we'll be in touch via email about probably we'll have a recitation section next week, but it'll mostly be focused on getting everybody set up with R and RStudio and the packages that you need and how to get the slides and stuff from GitHub and procedural things like that. Anyway, hope you stick with the class, and I'll see you around.